Welcome to our discussion of addition and subtraction of polynomials. So these are the concepts we're going to cover today, just the basics of what a polynomial is, how to add and subtract them, and then look at some of their applications to geometry. So let's first start off by introducing ourselves to what the heck a polynomial is. Now, I'm not a big fan of teaching vocabulary in a math class, but you need to know some of these terms just so when you see them in a textbook or whatever, you know what the heck they mean. A polynomial in one variable, normally x, is simply defined as a single term or a sum of terms where each term is of the form a to the x times n, or sorry, a times x to the n, which simply means each term, terms are things that are separated by pluses and minuses. They say sum because anything that's separated by a minus, you can think of it as adding a negative thing. So a would just be negative in that case. But each of the terms are just going to be a constant, right? A coefficient. A is called a coefficient. You just think of it as a number, a constant, and then a variable, in this case s. But you could have a polynomial in terms of t's or in terms of y's or z's, just as long as they're all one variable, you're good to go. You can also have polynomials in terms of multiple variables, but that gets more complicated. And for our purposes, we're just going to let it be one variable. But anyhow, you got to have a coefficient, a number, and then you have a variable raised to a power. That's it. And that power can be any non-negative integer. So what that means is the power can be 0, which of course means it goes away altogether because x to the 0 is 1, and then you just get a, you just get that constant. So a polynomial can have a little constant term at the end of it. N could be 1, so then you just get a x, right? And then it could be any power above that. So like I said, the a in front is called the coefficient. And then n, the largest power that n takes on, is called the degree of the term. Well, n is the degree of each term. The largest it takes is the degree of the polynomial. So for instance, if we have something like this, 6x to the 10th minus 3x to the 7th plus 4x squared minus 2x plus 10. You can see that I'm missing powers. And that's fine, right? You don't have to have every power from 10 down to this is x to the 0 because that just becomes 1. So the coefficient is 6, the degree is 10. The coefficient here is technically negative 3, and the degree is 7. Coefficient of 4, degree of 2. Coefficient of negative 2, degree of 1. Coefficient of 10, degree of 0. And we would say the degree of the polynomial is 10 because it's always the largest degree of any of the terms. So here's some more examples, right? Coefficient negative 12, degree of 7. X cubed you can think of as having a little 1 in front of it, right? That invisible 1. So its coefficient is 1, its degree is 3. 10 to the w, again, any variable that's just sitting there has an invisible degree of 1. And then the same thing if we have a constant, that's where the degree of the variable was 0. Now, if a polynomial has exactly one term, it's categorized as a monomial, like mono meaning one. I'm trying to think of a mono example of that word, but I'm sure you guys have. The monorail, right? It's a thing that runs along on one rail. It's Latin. Mon for Latin means one. And then if it has two terms, it's a binomial, like a bicycle has two wheels. And then if it has exactly three terms, it's called a trinomial, like a tricycle has three wheels, right? This is all Latin junk. 4 terms, we really stop at that point. We don't call it a quadrinomial. We just start calling them polynomials at that point. Okay, we've already talked about the term of a polynomial with the highest degree is where we get the degree of the polynomial, right? So in that example where I had 6x to the 10, this is considered the leading term because we always write our polynomials with highest degree first down to lowest degree, and then of course the constant is at the end because that would be lowest degree, degree of 0. And the reason why we do that is because then we get what's called the leading term and the leading coefficient. So in this case, leading term is 6x to the 10th, leading coefficient is 6, and the degree of the leading term is 10, and because the degree of the leading term is 10, that's the degree of the polynomial, right? It's the greatest degree of all of its terms, like I said, and so it ends up being the degree of the leading term when you put them in their proper order. And like I said, that proper order means descending order. So here are some examples of monomials, binomials, and trinomials. You can see that the first example, they're not necessarily in descending order, and then in the second column, we put them in descending order, which puts them in proper, polynomial form, and then by doing that, we thus know what the leading coefficient is, because it's always the number, right? The coefficient in front of that first term, the one that has the highest power, and then the power of that term becomes the degree of the polynomial. Okay, so just a lot of vocabulary junk, and it's really just so that you describe your polynomial the same way that I would describe the exact same polynomial, just so that we're speaking the same language, because then otherwise we get into a who's on first kind of thing where we're probably describing the same thing, but because we're describing them two different ways, we can't tell that it's the same thing, right? So that's why we have these rules in mathematics, is so that two mathematicians can describe the same thing the same way and thus know that it's the same thing. Example, given this polynomial, we can list the terms of the polynomial, state the coefficient and degree of each term, then we can write the polynomial in descending order. Once we do that, we can just state the degree of the polynomial and the leading coefficient, and then finally we can evaluate the polynomial for a equals -2. So listing the terms, that's pretty easy, right? A term is anything separated by pluses and minuses. So my terms are 3a, technically -2a to the fourth, right? Because it's supposed to be things separated by pluses, 6, and -a cubed. Those would be my terms. I could state the coefficient and degree of each term, right? Coefficient of 3, degree of 1, coefficient of -2, degree of 4, coefficient of 6, degree of 0, and finally coefficient of -1, degree of 3. Simple, easy. Okay, write it in descending order. Also easy. Find the highest power. So it's -2a to the fourth. Next power is the 3, so minus a cubed. There's no squared, so we go to plus 3a, and then finally plus 6. So there it is in standard polynomial descending order form. Now we can state the degree of the polynomial. It's the highest power, so it's degree of 4, leading coefficient of -2, and if we want to evaluate it at a equals -2, you're simply plugging that in. So -2 times -2 to the fourth minus -2 cubed plus 3 times -2 plus 6. You'll notice that I'm putting these in parentheses because when I let a equals -2, that entire thing goes in for a, and so the negativity is also getting raised to a power. So -2 to the fourth is -2 times -2 times -2 times -2, which gives us positive 16. So this is -2 times 16 minus, here we get -2 cubed. 2 is 8, right? So this stays negative, so minus a -8 plus 3 times -2, that's a -6, and then plus 6. Well, I'm going to go ahead and cancel those, right? Because a -6 plus 6 goes away. Now I can do the rest of my work. -2 times 16 is -32. Minus a minus becomes plus 8, right? And so then we get 24. So that's how we would work with that polynomial and those are pretty much all the types of things that you need to do with polynomials. You need to identify its bits and pieces, you need to identify its degree and its leading coefficient, and you need to be able to evaluate it at certain values. And then beyond that, you're also going to need to work with them. You're going to need to be able to add them and subtract them and multiply them and divide them. Well, adding is the next thing we're going to talk about. And it's really simple because you can only add polynomials that have similar terms. And remember, terms are things that are separated by pluses or minuses when you look at them. Remember that it's technically always separated by pluses because anything that's separated by a minus is technically adding that negative thing, because then that reminds us that the term has a negative coefficient. But in any case, you can only add things if the terms match except for their coefficients. So because these two things have the exact same shape, right? They have the exact same form except for their coefficients, right? Basically the variable pieces have to match. I have x squared y, I have x squared y. So I have 3 of these things and I have 5 more of these things. So I simply just have 8 of those things. And it doesn't matter if those things are an x squared or just a y or an x squared y or an x squared yz, right? As long as they were identical, then we just add them together. Same thing here. If I'm going to add this junk to the stuff on the left, I have to find matching stuff. So here is a C3, here's a C3. I've got 11 of them, minus 3 of them. I have 8 C cubed. Okay, so here's my C squared and my C squared. I have 6 of them here. I have 5 of them there. So I get 11 C squareds. I don't have any C's over here, so there's just minus C. And again, no constants to add, so plus 3. So as you can see, it's just matching up the terms that have the same shape, right? They have to have all everything except for their coefficients have to be the same. So all of the letters have to match. We can do it again. We've got a w squared here and a w squared here. So 4 and 3 is 7w squared. I have an x squared, but an x, right? I can't put those together. So I just have minus 4x squared. But this x can go with this x, and I have negative 2 plus 6 of them, so plus 4 x's. And that's how that would work. All right, let's look at subtracting them, which, subtraction and addition are the same darn thing. So if we know how to add polynomials, we surely know how to subtract them. Find the opposite of these? Well, that means just multiplying everything by negative 1. So you multiply through by negative 1, you get negative 3a plus 4b plus c, right? You get negative 5.5 plus, and this becomes a minus. Simple, simple, simple. So if a and b are polynomials, then a minus b is really just a plus the opposite, right? A plus the negative. We already knew this, right? Subtracting is always the same thing as adding a negative, right? 10 minus 3 is the exact same thing as 10 plus a negative 3. Doi, right? The reason why we do that is it just reminds us that when we're subtracting a whole polynomial, it's a lot easier. There's a lot less chance of making a simple mistake if we change this to adding the opposite. So instead of subtracting this whole thing, we're going to add the opposite. And the opposite means just change the sign of each piece. So we're going to add negative 11p squared. We're going to add negative 4p. And we're going to add 6. Right? Technically, if you wanted to do it in steps, you could just go add the whole thing, right? Negative 11p squared minus 4p plus 6. So even if you did it like this, it's still a lot easier for our mind's eye to kind of see what's happening and less chance of us making a mistake than doing this. Because what happens is we forget to distribute the minus onto everything, and we forget to subtract this piece, and more importantly, we forget to add this piece. But when we distribute that minus through and turn it into an addition, that's something our brain doesn't screw up. So we go, okay, I've got 4 of them here and nothing of them over here. So just negative 4p to the 4th. Then I've got a p squared and a p squared. So 5 of them minus 11 of them, so negative 6p squared. I don't have any other p's other than this piece, so minus 4p. And then I have a negative 3 and a negative 6, positive 6. 6 minus 3 is plus 3. And there is my subtraction. All right, let's look at another example where we're subtracting all of this stuff, and we can think of it as just distributing the negative. So it becomes adding a positive 1, negative, negative. So we're adding 6ab and then subtracting the 2b squared. And now we go, okay, I've got 1 of them, 8 of them, I've got 9 of them. I've got a 6ab and a negative 2ab, so that's plus 4ab, negative 2 of the b squared, 7 of the b squared, so plus 5 of the b squareds. Another example, if we want to subtract this from this and then simplify the results, so we're basically saying t squared minus 4 minus, right, when you say subtract from, we're taking this away from that. So we're subtracting 1/3 t to the 4th plus 1/2 t squared. When we're subtracting, right, we're adding the opposites, negative 1/3 t to the 4th minus 1/2 t squared. And now we can do our like terms, right? We've got 1t minus 1/2 of a t, I should say squared. So we have, well, let's start with the big power, put it in proper form. We have negative 1/3 t to the 4th. And then we put these t squareds together and we get plus 1/2 t squared, right, because 1 minus 1/2. And then minus 4, because there's no constant to add to it. And there it is. That's our simplified result in our proper polynomial form. All right, the last thing we want to look at is a simple example with a geometric shape. So if the perimeter of a triangle can be represented by the polynomial 2x squared plus 5x plus 6, we can find a polynomial that represents the length of the missing side because we know perimeter is just the three things added together. So basically, we know that whatever this is, right, that blank, has to be this answer minus these two pieces. So the first thing you could do is maybe add them together and then subtract them, or you could just subtract them in pieces. So here's 2x squared plus 5x plus 6. I'm going to subtract x squared and subtract 1 from it and be left with x squared plus 5x plus 5. And ooh, there's a new technique, right? You can subtract it just like you would subtract numbers, right? If you wanted to take 125 and subtract 13 from it, you just line them up, and 5 minus 3, 2 minus 1, 1 minus 0. There's my answer, right? I've got 2x squared minus 1x squared. I've got 1x squared. 5x, don't have any x's, so that just stays 5x. And then my constant minus my 1, there's my new thing. Now I can take this, and I could subtract 2x, right? And then add 3. You got to remember that when you subtract this, you're changing the sign. You're subtracting, but you're adding. So when I do that, I get x squared. 5 minus 2 is plus 3x. 5 plus 3 is 8. And now that I've subtracted these two pieces away, I know that this is the answer for that missing piece. So really, I mean, all we're doing is we're still doing some subtraction of polynomials. We're just giving it a context of a geometric shape. Usually what happens with geometric shapes and polynomials, it more often comes from multiplication. You'll have a square, and it'll be something like this is x plus 2, and this is 3x minus 1. And they'll say, what's the area of the square? And you got to do this times this. But that's something for another lesson. This is everything I got for you for today.